All right, everyone. Today, we're going to tackle a huge concept, the idea of empty. We're diving straight into the quantum vacuum, and you're about to find out that what we think of as nothing is pretty much the foundation of everything.
So let's just get right to the heart of it. Is empty space really empty? I mean, what if a perfect vacuum, a space with supposedly zero matter, is actually one of the busiest places in the universe? Well, quantum mechanics has a truly mind-bending answer for us.
So here's our game plan for this explainer. First, we have to completely redefine what a vacuum even is. Then, we'll dive into the quantum fields that basically make up reality. From there, we'll see how the famous uncertainty principle guarantees that this so-called empty space is anything but quiet. We'll look at the actual proof. And finally, we'll explore what this all means for the cosmos.
Okay, first things first. To really get what's going on in the quantum world, you have to kind of throw out the old intuitive idea of a vacuum. This notion of it being just absolute nothingness, it just doesn't hold up in physics. We need a much better framework.
And this slide really nails that critical shift in thinking. On one hand, you have the classical idea. A vacuum is just the absence of everything. Simple. But in quantum mechanics, the vacuum is a presence. It's defined as the lowest possible energy state a system can have, what we call its ground state. So think of it this way. It isn't an empty room, it's the very floor of the room itself.
So that raises the question, right? If the vacuum is the lowest energy state, then it's the lowest energy state of what? Well, to answer that, we have to talk about what the universe is actually made of at its most fundamental level, quantum fields.
The best way to get your head around this is with an analogy. Imagine the entire universe is filled with a vast invisible ocean. Now, this ocean isn't in space. In a very real sense, it is space. And every fundamental particle has its own ocean, its own quantum field that permeates every single point in reality.
So if the field is the ocean, what's a particle, like an electron? It's not some little ball floating on the ocean. No, a particle is a piece of the ocean. It's just a localized ripple, a little vibration, an excitation. A particle is just a wave on its corresponding field.
And this brings us right back to our main question. If particles are the waves, what do you call the field when there are no waves? What is that perfectly calm, completely undisturbed ocean?
You guessed it. That calm ocean is the quantum vacuum. It's the field just existing in its most fundamental lowest energy state. It's the absolute baseline of reality, and it's present everywhere, even when there are no particles around.
Okay, but here's where things get really interesting. There's a fundamental rule baked into quantum mechanics that says this quantum ocean can never be perfectly calm and still. There's always this subtle, underlying restlessness.
And that rule is the Heisenberg uncertainty principle. Now, you've probably heard about it with position and momentum. The more you know one, the less you can know the other. Well, that same principle applies to other pairs of properties, and the crucial one for us right now is energy and time.
This has a massive consequence. Since you can't have a perfectly fixed amount of energy, like zero, over any slice of time, nature allows for a bit of wiggle room. For incredibly short moments, the vacuum can essentially borrow a tiny amount of energy as long as it pays it back almost instantly. This constant borrowing and returning creates a simmering activity we call quantum fluctuations.
So what does this borrowed energy do? Well, E equals mc squared, right? Energy can become matter. This borrowed energy briefly bursts into existence as pairs of virtual particles, an electron and its antimatter twin, a positron, for example. They pop into reality out of the field, and then, almost instantly, they find each other, annihilate, and disappear right back into the vacuum. So empty space is actually this roiling, seething foam of particles popping in and out of existence.
Now, I know what you might be thinking. This all sounds like a weird mathematical quirk, some abstract idea. But the crucial thing to understand is that this isn't just theory. This activity of nothing has real, physical, and measurable effects. We can actually see its fingerprints in the lab. And this is always the most important question for a scientist to ask, right? It's a fantastic theory. But where's the proof? How can we possibly be so sure that this invisible world of virtual particles actually exists? Well, we have some absolutely stunning proof. First, there's the Casimir effect. If you take two uncharged metal plates and put them incredibly close together in a vacuum, they actually get pushed towards each other. Why? Because the virtual particles popping into existence outside the plates create more pressure than the ones that can fit between them. The vacuum itself is pushing them together. Then there's the Lamb shift, a tiny but perfectly measurable nudge in the energy levels of an atom's electrons. And what's nudging them? The constant jostling from all those virtual particles in the vacuum. Okay, so now that we've got solid evidence this is a real thing, let's zoom out a bit. Let's talk about the cosmic scale and clear up some of the biggest questions and misconceptions about the quantum vacuum.
This is a huge one. People often talk about this as getting something from nothing. And we have to be super clear. The quantum vacuum is not nothing in the philosophical sense. It's a complex physical system. It's already packed with quantum fields, it has potential energy, and it's governed by the laws of physics. It's the baseline state of a very sophisticated something.
Now for the truly mind-blowing part. Those tiny microscopic quantum fluctuations we were talking about? Cosmological theory suggests that in the very, very early universe, those tiny jitters were the seeds for everything we see today. Those tiny variations in energy and density were stretched out by cosmic inflation, and over billions of years, gravity sculpted them into the galaxies and the vast cosmic web we see today. From the tiniest flicker came the largest structures in existence.
And just for the sake of clarity, it's really important to separate the established physics from more philosophical ideas. You'll sometimes hear these concepts get linked to things like the vacuum being a form of consciousness, or that our minds create reality. And while those are fascinating ideas to think about, they are not physics. The scientific view is that the vacuum is a system of physical fields that behaves according to testable mathematical laws.
So, what's the big takeaway from all of this? It's that the universe is just so much stranger and more alive than it appears. The space we call empty is, in fact, the dynamic, energetic engine room of reality. The vacuum is not empty. It is the hidden foundation of everything. And that really makes you wonder, what else might be hidden right in plain sight?